Welcome back to matrix operations. This might be the first session where you encounter stuff that you haven't seen in high school yet. And so it might be also helpful to go back to the vector calculation slides after you watch this, because there you might understand why a vector is technically nothing else than a small matrix, and why specific operations on a vector can happen, cannot happen. And so the operations here on the matrix go into more detail and are more complex and complicated to understand. So a really important thing to differ here when we talk about the identity of a matrix. A matrix is, from a mathematical perspective, identical if we do some operations to it. So we can interchange two rows in this matrix. We can multiply all the elements in a row with a real number that's not 0 to change the values in the matrix. And we can add multiples of the elements of one row to the elements of another row. And from a mathematical perspective, nothing changes. However, as we're in economics and numbers have meanings, they are connected to trade flows, they are connected to people. It is really, really important that if you do such changes, you change the economic meaning. From a mathematical perspective, you're totally fine, but from an economic perspective, be really, really careful if you do mathematical changes to a matrix which keep it identical from a mathematical perspective. It might not be the same matrix afterwards from an economic perspective. But on mathematical calculations, we've seen the vector addition, how that adds up. A plus B equals C, and B plus A equals C. And the same applies to matrices if they have the same dimension. And it looks pretty much like this. You have the matrix A plus the matrix B gives matrix C. And if we add up the element A11 with the element B11, you get the element C11. It's quite simple. This is basic first grade math. Easy peasy. It gets a little bit difficult later. Don't worry. Scalar multiplication. Same as in a vector. You have a number. You multiply it with a matrix. Every element in this matrix is multiplied with the scalar. You scale the matrix. So now we're getting messy. We have matrix multiplications. And matrix multiplications, you see this in the first line here, to get to the matrix C with the dimensions M cross P, and you want to multiply the matrices A and B to get to that C, the matrix A must have the dimension M cross N, and the matrix B N cross P. So be really, really careful here. This means that, for example, just because you can multiply A and B to get C does not mean you can multiply B with A. This only works if both of them are quadratic. But otherwise, if you have rectangular matrices, this will not work. And the reason for that is really, really messy here. We're not just multiplying the element A11 with the element B11. No. What we're actually doing for the first element in C, so C11, is the first row of matrix A. So A11, A12, A13, and so on. We multiply that with the column of B1. So A11 times B11 plus A12 times B21. And so on. And that gives you the first element of C11. It's extremely messy if you think of that. If you have a huge matrix, 70 times 82, with multiplying with another matrix of 82 times 120, good luck doing that by hand. We're really glad that we have computers for that. And really, I can't stress it enough. It's really, really important to consider the dimensions and to be aware that multiplication with a matrix is not symmetrical, as you might have seen in regular math. 5 times 3 is the same as 3 times 5. This does not apply to matrices. However, there is a thing of an header multiplication. You barely see that, but just for completion, I want to show this here to you. You see the multiplication sign has a circle around it. That's the sign that it's a header multiplication. Here, the matrices must have identical dimensions. So the matrix A and B must have the same dimension, because what we're actually doing is that the corresponding element is multiplied with each other. So that's the math that you're familiar with. A11 times B11 gives C11. This sounds super easy and simple, and spoiler alert, we're not going to use that at all. So it's here for completion, that you know that it's possible, that you can go back to it, but we will not use it, because why would we use something that simple if there's more complicated stuff to look into? Similar to a vector, you can transpose a matrix. So we switch rows with columns, and this is also the same way as we've seen earlier, why it is possible to write vectors vertical and horizontally. So the matrix A with the dimensions m cross n transposed gives the matrix A with the dimensions n cross m. So you just switch rows and columns, nothing big and fancy. Vector multiplications, a little bit more difficult. It makes sense if you understand a vector as a small matrix, because here you can multiply the vector x with the dimensions n cross n with the matrix A in the dimensions n cross m. So after that, you get a matrix with the dimension 1 cross m. And so this is something where you see and understand, hopefully, why a vector is nothing else than a small matrix. And we can also multiplicate a matrix with a vector. And you're like, wait, this is what we just looked at. No, it's different, because multiplication in matrix algebra is not symmetrical. Just because you can multiply a vector with a matrix does not mean you can multiply the matrix with a vector, because you have different dimensions. And you see, I'm stressing the point of dimensions, really important here. If you throw in matrices and vectors into a math program, Mathematica, R, or whatever you're using, MATLAB perhaps, and you try to multiplicate something that has not the same dimensions, you're in deep trouble. Even your computer can't solve that, because it's mathematically impossible to do so. Now we're getting even more messier, because, you know, matrices are difficult, and so we also need difficult math. And we can look at the inverse of a matrix. The requirement to have an inverse of a matrix is that the matrix is quadratic and invertible. Well, this is a definition that lacks some understanding. Of course, to get the inverse, it must be invertible. But the idea of the inverse is that if you have a matrix and you multiply it with its inverse, indicated to this -1 in the exponent, you get the identity matrix. So if we have the matrix 3, 7, 2, 5, we need to find a matrix with the values. Here I give you already the solution, 5, -7, -2, and 3, which, if you multiply the two of them, you get the identity matrix. It's quite interesting to see. Here, the symmetry aspect plays out as well. You can switch the inverse matrix to multiply it with the original matrix and still get the identity matrix. This is quite the run-through, like in an inverse, but I want to show you an example, and especially in a 2 cross 2 matrix, how you get there to calculate this inverse. So here we have this matrix A, B, C, D, and its inverse can be quite easily done in your head by Cramer's rule. You have the first element of the inverse of M is the element D over the multiplication of A times D minus BC. So you always see here in the fraction below the line that you have AD minus BC. You switch the elements A and D in the fraction above, and you just multiply the elements B and C with -1. So this is how you get, with Cramer's rule, the inverse of a matrix. Let's say you have a matrix which is larger, 3 cross 3. Well, things get extremely messy, and thank God we're not doing that by hand anymore in the 21st century. We have computers there, and that use normally an algorithm with row operations, which we skipped here completely because it's mathematically of interest, but not in economics, or with the adjoint matrix, where you can do that, which is extremely calculation intense. And this is also the aspect why we will not be probably talking about that here. We just say like, okay, we've done it once for a 2 cross 2. I see where this is coming from, and everything that I use, I take the black box my computer gives me and work with that. There's another aspect that is really, really important in matrix algebra. We want to look at the determinant of a matrix, and the determinant of a matrix incorporates all the elements of a matrix and reduces the matrix to a single number. So whatever this M cross N matrix is, we can write it in one single number and do fancy math with that later on, because we stored this complete matrix into a single value. There are some requirements to calculate the determinant. The original matrix must be quadratic. So the example I gave you, the matrix M cross N, you know already it's N cross N. And the determinant can be 0. But if you have a determinant of a matrix which is 0, then by definition, all the stuff I showed you a second ago with invertibles of a matrix is not possible. It's a mathematical requirement that if the matrix is invertible, the determinant cannot be 0. So that's an easy cross-check to figure out if you actually can calculate the inverse or not. And even here, a little bit calculation intense, but we can do this quite easily on a 2 cross 2 matrix. And even a 3 cross 3 matrix is simple. So for a matrix of the dimensions 2 times 2, the determinant is multiplying the first element, A11, with the element A22, and we subtract A12 times A21. And if you're thinking about this, this sounds familiar, this phrase, A11 times A22 minus A12 times A21, because that's what we just had in the inverse in the fraction. And this is the reason why the inverse cannot be calculated if the determinant is 0, because then you have a fraction with 0, and that's mathematically not possible. If we go at the 3 cross 3 matrix, we can apply the rule of Saros just for completion, where we multiply elements, subtract them from each other. This is something you can still recall if you want, but we're getting here at a point where it's already quite mathematically calculation intense. That's not something you do on the back of a receive or something like that to calculate this determinant. And there are also ways to calculate larger determinants of larger matrices. But this is really, really calculation intense. This is something you do for fun if you go for a math degree. But for us here, again, I highly recommend to take the black box your computer gives you. And if you're really, really curious, Mary Jane Sterling has in her book a really great example on page 189, where she shows you larger dimension matrices and how to calculate your determinant there.